It should be on now.
Yeah, so this morning we'll begin with a talk by Brendan McBennett, who's an expert on nanoscale phonon transport. And yeah, I guess maybe he'll talk about some of the work he's doing with collaborators all over the world and industry, academics, etc. So
Great. Yeah, thanks so much, Andy. And I'm Brendan McBennett. I'm currently doing a postdoc at NIST, the National Institute of Standards and Technology, right across the street. I did my graduate work in Margaret's group, who you heard from yesterday. So we'll be talking a little bit about the same EUV high harmonic generation sources that y'all were talking about yesterday. And I guess, like, can everybody hear me okay? And, also feel free to just stop anytime and ask questions throughout the talk. We have plenty of time to, talk about things, whatever direction y'all want to take it in. So first, I'd like to thank all my former group members at the University of Colorado, my new coworkers at NIST, and a lot of our theory collaborators whose work has all gone into some of the stuff that we'll talk about today. And so, this is part of the lectures that Margaret was giving this week. Yesterday, y'all heard about high harmonic generation and the coherent imaging. Today, we're going to talk about nanoscale thermal transport and also some about some of the theory and also how you measure this experimentally. And then later in the week, spin and many-body electron phonon dynamics. So for the outline for today, first I'll give a little bit of an overview of phonons and what we mean by phonons in sort of the context of nanoscale phonon transport. What kinds of phonons are we talking about? Then I'll get into kinetic transport theory. This is kind of the backbone of how you connect microscopic information about phonons to macroscopic equations like Fourier's law and the heat equation, things like this. And then I'll get into phonon transport at the nanoscale, talk about a couple of examples experimentally and theoretically, and how we might measure these sorts of things and where are the applications for knowing about phonon transport at the nanoscale. So just starting out with sort of the textbook idea of a phonon, this you'll find in sort of any condensed matter solid state textbook. You have a one-dimensional chain of atoms with some lattice constant A, and you're connecting these atoms basically with springs. So you have this harmonic potential with the atoms. And we're going to have N atoms in the chain. They have a mass N. We'll set the lattice constant to 1 to make it a little bit simpler. And then we have this variable U sub N, which is the displacement of an atom about its equilibrium position as it's sort of connected to these Coulomb forces, these springs between the atoms. We have a finite chain, so we're going to put in a periodic boundary condition on this system. And we can write down a Hamiltonian, and this is sort of your standard classical Hamiltonian for N harmonic oscillators. We can also then write down an equation of motion, which relates the second derivative of the atomic motion to the positions of the adjacent atoms. You can now sort of have this differential equation of motion. You can postulate, you can sort of set a wave solution to this equation, guess that the solution is a wave here on the top left or top right. We have the laser pointer. And then you can basically say, okay, well, we have our boundary conditions. These boundary conditions are going to set the possible wave vectors that we can have in the system. So K, this wave vector, which will show up a lot today, is sort of a continuous, or it's a discrete variable rather than a continuous variable. And finally, we can solve for dispersion. And this is sort of the classic dispersion of a one-dimensional atomic chain that you'll see in textbooks. And it relates the frequency of the phonons to the wave vectors. And here you can see it's a sinusoidal relationship. But if we had a very small wave vector, so a very long wavelength, this is actually pretty much linear. And this is the idea of an acoustic phonon. So far, so good. This is all classical. And now we can ask, well, what if it's a quantum mechanical system? Because ultimately, you hear the definition of a phonon, and it's sort of this quantized lattice vibration. So how does this work in quantum mechanics? And the answer is basically, and I won't go into all the details here, you have a bunch of harmonic oscillators, quantum harmonic oscillators, and you superimpose them all. You can solve this out, write down a Hamiltonian, and you ultimately are using the same kind of framework that you'd use for any other harmonic oscillator, like ladder operators and creation annihilation operators, all this sort of stuff. And what we say here when we arrive at a solution is we have a Hamiltonian, and we have a frequency of the phonons. This is the dispersion coming in, and then this n sub k is exactly what you see in the quantum harmonic oscillator solution. And we would say here that mode k has n phonons in the mode, depending on how much energy is in that mode. So it's really similar to like photons in a cavity, basically. Just real quick is, for n atoms, we have, in 3 dimensions, we'll have 3 n phonon modes. So we have a whole lot of different modes, especially for a large macroscopic crystal. You can see how this will computationally can be really difficult once you start building up macroscopic objects of phonons. And one last thing here to point out is that so far, all the equations we've been writing down, all these Hamiltonians are harmonic. So we're using second order in the atomic potential, second order in the displacements of the atoms. And in this kind of situation, the phonons are sort of corresponding to the eigenstates of the Hamiltonian. And these are energy eigenstates, and so they're not changing under time evolution. And as a result, you basically you have infinite phonon lifetimes. Like you have a phonon and it's not scattering with anything, it's just going on and on and on. And this isn't accurate. We know that phonons scatter with other phonons. They scatter with imperfections in the crystal. They can scatter with boundaries. They can have all kinds of different ways that phonons are created and destroyed in a crystal. And so in reality, the atomic potential that the phonon sees is actually anharmonic. You have a lot of additional terms in the potential, and this is what gives phonons their finite lifetimes. And this is one of the things that also makes phonon transport complicated, is you have to deal with anharmonic potentials, finite lifetimes, and sort of figure out what these lifetimes are in various crystals. What is the lifetime of a phonon in a nanostructure versus in a bulk system versus all this kind of stuff. So yeah, feel free to stop me if we have any questions. That's kind of the overall intro to what is a phonon kind of in a condensed matter textbook. So now we're going to move to real materials. This is diamond. All of a sudden, we have a dispersion that has multiple branches. Looks a lot more complicated than a one-dimensional atomic chain. The black lines here are the theoretical predictions. The squares here, the diamonds here, are the experimental measurements. And you can see, all these multiple bands are coming. Some of the multiple bands are coming from different polarizations. So in 3 dimensions, we can have a particular wave vector of a phonon, and you can have longitudinal polarizations. So the atoms are oscillating about the direction of travel. You can also have transverse polarization. So the atoms are oscillating transversely to the direction of travel. That's giving us these multiple polarizations, multiple bands. We also have, we'll start talking now about various phonon properties. Yes?
Did you say how are these measurements taken? Is this measurements data or simulation?
The simulation, the black lines are simulations, and I think the measurements are probably, I don't actually know how they did these ones in this paper, but this would be some kind of probably Raman, some related kind of thing. So phonons have different properties. Here we have the phonon group velocity, which is the slope of the bands. You can kind of see that over here with this group velocity. So very steep bands will have a high group velocity, phonons traveling very quickly. Phonons have lifetimes, and this will sort of correspond to the thickness of the band, the width of the band. Very broad bands versus very short bands. And we have these various types of phonons. And so I've sort of color-coded it here. The acoustic phonons have very short, very low frequencies. And these very low frequencies, and they have very long wavelengths and short wave vectors. And these have approximately a linear dispersion. And these are the kind of like kilohertz to gigahertz phonons that we think of as propagating sound in materials. So they're very much, you can think of them as waves. And these are basically moving sound from one point to another in a material. And they're pretty well behaved. You can model them with wave mechanics. Then up top here, we have the optical phonons. Optical phonons have very high frequencies. They have low group velocities. You can see these bands are pretty flat. And you can kind of think of this as like very quick oscillations within a particular unit cell of the crystal. So you might have a unit cell or a basis, and the atoms in the basis are vibrating in opposite directions. And they have a really high heat capacity. You can store a lot of energy in an optical phonon up here, high in the dispersion. But they don't have a very high group velocity. And so in terms of talking about phonon transport, the optical phonons don't play a very large role a lot of times because they have such a low group velocity. And so in the middle here in yellow, we have thermal phonons. This is kind of, a very imprecise definition. This is sort of color coded to make a point here, but there's not a precise definition of what is a thermal phonon. But in many materials at room temperature, thermal phonons have a roughly a frequency in the terahertz range. So from a couple of terahertz all the way up to tens of terahertz. And these are the phonons that are really moving heat around in a crystal. And this is something that's of a lot of interest for all kinds of different technological applications of, how do you get heat out of a semiconductor? How do you get heat through a thermoelectric device and all this sort of stuff? There's one more definition I want to make here, and that's this idea of a phonon mean free path. And that is if you know the lifetime of a phonon, so sort of statistically on average, how long does it take a phonon to scatter with another phonon, with an imperfection, et cetera, and the velocity of a phonon, which is not so much a statistical quantity, it's sort of a known quantity, it's a harmonic quantity based on the lattice, then you can multiply these two together and you get a mean free path. And this is the distance that a phonon typically travels before it undergoes some collision event. And this is a very important quantity we'll see for thermal conduction in crystalline materials and in semiconductors. And this is a statistical quantity. So for example, the mean free path that you have in a large bulk system is going to be very different than the mean free path that you have in a small nanostructure where the system is very confined. And you can't travel more than the distance across the nanostructure. So now just real quick to review, we're talking about phonon transport, and ultimately this is the microscopic version of the macroscopic idea of thermal transport, which is sort of in this case, it's heat conduction in a solid. And macroscopically, we have a couple of equations. Fourier's law, which says that the heat flux Q is proportional to the temperature gradient through some thermal conductivity. And then we also have the heat equation, which is a differential equation for the temperature. And these have all been known for some time. And a lot of what we'll talk about today is how do we relate these macroscopic equations for thermal conduction to the microscopic information that we know about phonons, like group velocity, lifetime, frequency, and mean free path. And we know, based on experiments and stuff that we'll get into later, that these macroscopic equations, using all of these sort of bulk values of thermal conductivity and whatnot, these break down at the nanoscale. And you need to resort to these microscopic descriptions to come up with new laws and new theories and new models of phonon transport. And so that's kind of what you're trying to do, is come up with something using the microscopic information that can explain physics at the mesoscale. So that's kind of talking a little bit about phonons, how they fit into this picture, what kinds of phonons are we interested in here. And now I'll get into kinetic transport theory. And the idea behind kinetic transport theory is how do we relate this microscopic information about the phonons to the macroscale information about where's the heat going, what is the temperature doing, and what is sort of the overall behavior of the system on a thermodynamic scale. So yeah, any questions so far? Yes.
So the acoustic phonons has larger group velocity. Why don't they carry the heat?
That's a great question. I think my understanding, and I could be giving you an incomplete answer here, but my understanding is they don't have a particularly high heat capacity. And also some of them are, And so I think for that reason, they don't necessarily carry a very large amount of heat. But I think it is more complicated than that. And in materials like graphene, you have a lot of like crazy acoustic phonon modes that aren't necessarily populated at certain times. And there can be questions of people don't really know why there's not more. But for that is a really good question. Great. So kinetic theory, what we're going to start out with now is we're going to treat the phonons all as particles. So up until now, we've been thinking of phonons as waves. They have a group velocity, they have a dispersion, they have, we're using things that look like the wave equation, or look like basically atoms on chains and things like this. We're going to now treat them as particles. And there's a couple motivations for this. The first is that phonons have pretty short wavelengths by the standards of many of the things that we're trying to measure. A typical wavelength at room temperature for a phonon in a semiconductor is around 1 nanometer. And so, if you're in a relatively large bulk crystal, you don't really have to worry about the phonon wavelength. You can kind of think of it as a particle. Also, you can have this idea of phonons interfering with each other. Maybe you have two phonons that are superimposed and they're interfering with each other. But a lot of times in materials, they have rough boundaries and the phases of the phonons are kind of randomized. And so you really don't have coherence with the phonons in a lot of materials at room temperature. And so all of this can motivate us to think about phonons as a particle rather than a wave. And that's what kinetic transport theory does. Another thing that's interesting with phonons is that you're conserving energy of the phonons, but you're not necessarily conserving that much else. And that's what makes phonons, that's one of the things that makes phonons a lot more difficult than something like an electron or spin is that you don't have as many conservation laws to rely on. So for example, the number of phonons is not conserved in a crystal, whereas you would have the number of electrons be a conserved quantity. And phonons don't have charge, so you can't manipulate them with a field. And so what we have is this idea of a distribution function. The phonon distribution function is saying, here in this case, this n sub k x of t it's the number of phonons with wave vector k at location x in the crystal at time t. And so you can kind of think of these as little wave packets, and these little wave packets are small relative to the size of the box x that we're kind of drawing in phase space around these phonons. And in equilibrium, since phonons are bosons, they don't have a spin, we can write down this equilibrium distribution function n sub k of 0. And this is the Bose-Einstein distribution function at whatever local temperature you're at in the crystal. And so this is ultimately, this Bose-Einstein equilibrium distribution function is what we're always relaxing back to, what we're always equilibrating to after some excitation in the crystal, like a laser pulse or something gets the system out of equilibrium. And then we go back to this equilibrium distribution function for a boson. So far so good. Now I want to talk just a real brief aside about conservation, because you might have seen, well, energy is conserved for phonons, but what about momentum? That's something that we would pretty much expect to be conserved for a lot of different excitations and quasi-particles. And the idea is that if you have a phonon in a crystal, the net positions of the atoms aren't changing as the phonon propagates across the crystal. Like at the end of the day, the crystal is still sitting on the table and the atoms are still in the same net equilibrium locations. They're oscillating about their equilibrium positions, but the atoms haven't moved anywhere. And as a result, we don't talk about classical momentum, sort of like mass times velocity. Instead, we talk about this quantity crystal momentum, which is h bar times the wave vector of the phonons. And crystal momentum is a little bit weird. Crystal momentum is only conserved up to a reciprocal lattice vector. So when you have a phonon collision process, you have two phonons come in and one comes out, or one phonon goes in and two come out, whatever it might be. You can actually introduce a reciprocal lattice vector into the conservation. And this has to do with the idea that ultimately, and we can sort of watch this GIF here to get an idea, is that there's multiple different phonons that well, let me explain it maybe this way, is that below a lattice vector, so below A, the lattice constant, the idea of wavelength is kind of meaningless. Like you could have all different kinds of wavelengths, but as long as the wave is the same at the location of the atoms, they're all basically the same excitation physically. So these three different curves that are appearing here with the atoms, they're all ultimately the same physical excitation. And so this is the idea is that you can have two phonons with a lot of crystal momentum, then that means that they have, or you can have two phonons with a certain crystal momentum produce a phonon with a really, really short wavelength, like this purple curve here, this orange curve here. And this really short wavelength is actually equivalent to a phonon of a longer wavelength. Because ultimately all you care about is the, what is the displacement at the locations of the atoms? Like you only have translational symmetry at the locations of the atoms in the lattice. And as a result, these phonons, these crystal momentum isn't conserved. Globally, it's sort of only conserved up to a reciprocal lattice vector. And so we have this idea of normal collisions where you have two phonons collide and then they produce a third phonon with the same crystal momentum as they had before, the sum of the crystal momentum here for normal collisions. And then we also have this idea of umklapp or resistive collisions. And this is where you actually do introduce a reciprocal lattice vector because you've produced a phonon with such short wavelength that it's equivalent to a longer wavelength phonon. So any questions about that? That's a little bit of a concept, but it just gives you an idea of how the conservation laws are a little bit different for phonons versus electrons. Yes, yeah. Oh, they also have the umklapp? Yeah, or like block. Oh, okay, yeah, I guess it's also the periodic potential there. So this is, I guess I'm thinking for electrons about like absolute momentum, and phonons don't have that. They have this sort of crystal momentum, which is a little bit, which electrons have too, but yeah. No, it's a really good point. That's a really good point. So now we get to this idea of the Boltzmann transport equation. And this is the idea of you're thinking about all the phonons as quasi-particles in the system. And you have all these phonons as particles, and you can model them the same way as that you'd model particles in a gas, basically, with a few modifications to the equation. But ultimately, this Boltzmann equation is sort of the statistical mechanics equation that governs the evolution of the distribution function in time. So this distribution function in sub k xt is evolving in time, and it's evolving as a result of two terms here. We have a drift term, which is just the phonons propagating at a certain velocity, at their velocity, without colliding with anything. And you also have a collision term, and this represents all the different ways that phonons could collide with other things in the crystal. So you could have phonons that collide with imperfections in the crystal. You could have phonons that are scattering off of other phonons. You could have phonons that are scattering off of boundaries. And the collision operator is a really difficult sort of thing to write down in a real crystalline system because there's a lot of different sort of material, or there's a lot of different terms and considerations and things that can all go into this. So I kind of wrote down an example term here for a 3-phonon process, and you have conservation of energy here. You have a matrix element, you have the different occupations of the different phonon modes that are colliding. But ultimately, solving for all this in a real crystal, especially without linearizing it first, can be very, very difficult. Yes?
Okay, what are the omega prime?
Oh yeah, these are the frequencies of the 3 phonons involved in the process. So in this particular process, we have a phonon coming in with a wave vector k and a frequency omega, and then a phonon coming in with a wave vector k prime and a frequency omega prime, and then they're colliding and they're producing a phonon with a wave vector k double prime, and ultimately energy has to be conserved, so we have a delta function here.
No, I just meant the factors of omega in front of the delta.
Oh, the omega is in front of the delta function. I think that this is some kind of derivative when you're deriving the collision operator, but I don't know totally off the top of my head where it comes from. But it's like sort of a textbook form that you have the energies out front too.
I guess it depends on the type of phonons you maybe have.
Yeah. In terms of like, yeah. Yeah, because everything else kind of makes sense. Like you have a matrix element, you have occupation numbers, you have energy conservation. I think that comes out somewhere in the derivation, but I couldn't tell you exactly. Yeah. Yeah, I think it's,
When you put in M.
I mean, I guess it's a.
Yeah, exactly.
Nonlinearity, cubic nonlinearity, like gradient of u to the cubed or something like this.
yeah,
Third order and the,
because this is the third order anharmonic term.
right, and then that
Yeah.
gradient is the translates into omega.
Yeah, yeah, that makes sense. So a couple of extra things to get out of the way here. And this is where we're going to start relating these microscopic quantities we've been talking about to macroscopic variables, is we have an energy density that we can write down. This is the energy per unit volume. We're summing over all the modes. And we have the distribution function for each mode, the number of phonons in each mode times the energy gives you a total energy. We also have a heat flux density, and this is the sort of the same as the energy, but we're adding in the velocity to get a vector quantity. How much heat flux per unit volume are we producing? And these are sort of absolute quantities, or these are sort of basically fundamental expressions. We haven't really made any assumptions yet. And we're going to get into some assumptions when we start deriving things like the thermal conductivity. So now I'll do a little bit on the chalkboard, because what we want to do is just show an example of how do you go from the Boltzmann equation to sort of like a Fourier law, which is ultimately what you have for sort of a macroscopic expression of thermal transport. So just feel free to stop me if you have any questions, and I can just do this one out. And then this can kind of serve an example of all the more complicated transport laws we'll talk about later when we get into the experiments. So I guess first off, I'm going to write down the Boltzmann equation, and we're going to do it in one dimension, and we're going to do it in the steady state. So we're going to ignore the time. We're going to set the time derivative to 0. So starting off, we just have this v sub k, and this is now just in the x direction. And we have a d n sub k, dx. And this is equal to the collision operator acting on n sub k. And so I haven't made any like major approximations or simplifications yet, but we're definitely going to have to make some simplifications in order to get to Fourier's law. Can y'all see that okay? Should I write bigger? Bigger? Okay. Let me erase that and do this a little bit larger so that we can all see it, because it's only like 5 or 6 lines. Okay. So we have a velocity. Is that better? It'll be big, but it's not too much math. It's not too bad. So we have velocity, we have a space derivative of the distribution function, and then of course we have the collision operator acting on n. And this is steady state. And it's 1D. Okay. And the very first thing we're going to want to do is we're going to make something called the local equilibrium approximation. So that's one of the 3 approximations we're on the slides. And the local equilibrium approximation basically says that d sub nk dx, so this is the x gradient of the distribution function. And remember, the distribution function's some crazy function of x, t, and k, and all these different things. So it's like we can't really write down a form for it very easily here, but the local equilibrium approximation we're going to make is that the distribution function is equal to dn sub naught, k naught, dt, dt dx. This is what's called the local equilibrium approximation. And so and what this is basically saying is that in a particular region of space, about x, you have basically a well-defined temperature. And this is a big approximation, because the idea is basically in a particular region around in space, you have a bunch of different phonon collisions, events, all kinds of stuff going on. But ultimately, all these sort of scattering processes they're happening so fast and so and on such small scales relative to the length scales you're considering in the problem, that you basically have a well-defined temperature, and you can sort of approximate your distribution function by the Bose-Einstein distribution function at that well-defined temperature. That's all we're saying here. And this is sort of a core component of Fourier's law. And getting to these macroscopic equations is you have to ask yourself, if there's a ton of phonons in a region of space, what does temperature even mean? Like, how do you define temperature? And so what we're saying is that all those phonon processes are happening so quickly that the temperature is actually sort of defined locally in a sort of convenient way. And of course, this dt dx is equal to the temperature gradient. So this is sort of an obvious component of Fourier's law. So now we're going to, what are we going to do next? We're going to make one more big approximation. And this is called the relaxation time approximation. So far we've been approximating the drift term. Now we're going to approximate the collision term. So you see you have to make a lot of approximations to get to Fourier's law. And the collision term, we're going to write C sub nk. And we're going to say that this is equal to, or approximately equal to, because we're making a big approximation here, is this is approximately equal to minus nk minus nk naught over some tau. And so what are we saying here? We're saying, and this is the relaxation time approximation, or you'll see it a lot in the literature as RTA. And so what are we saying here? We're saying that all the different modes, so all the different Ks, which would be coupled all kinds of easy ways in this collision operator, are evolving independently. So mode K doesn't care what mode K prime is doing, or K double prime, or anything like that. Each of them is evolving independently, and each of them is evolving towards the equilibrium distribution with a characteristic relaxation timescale tau. And I've made an even further simplification here is that this is just one number for every mode. So every mode is relaxing towards equilibrium at the same rate. So this is a huge approximation. It doesn't even conserve energy in a lot of contexts, but it's a very useful approximation, and people make it for a lot of different kinds of, in a lot of different contexts, also for electrons. And it's ultimately what's going to get us to Fourier's law. And in the sense of the scattering, it's like, what it's basically saying is that you don't have a lot of like normal scattering, redistributing energy and sort of whatnot between modes. You basically have a lot of resistive scattering at this very characteristic time scale, bringing you towards equilibrium. So any questions so far about these approximations? Or is this all good? Because from here, we'll sort of just plug it in and it'll work out. But these are some of the big ones. Cool. So then we can write down, just so we have it on the board, nk naught is equal to, this is this equilibrium distribution function. This is equal to e to the h bar omega k over kvt. And of course, this t depends on x and time, -1 to the -1. So this is our Bose-Einstein distribution function. Great. So now we're going to sort of just plug this all in. We have v sub k. We've made our local equilibrium approximation. So d k naught dt dx is equal to, and now we've put in the relaxation time approximation. And we have this. And now what we're going to do is multiply both sides by a fair amount of constants, or not constants, phonon properties here. So we're going to multiply everything by h bar, omega k, and v sub k. And so we get a v sub k squared over here. And so we have d sub k naught over dt. And then we'll just write this as the temperature gradient is equal to, and now h bar, omega k, vk, and now we have, again, the tau here, and then the nk minus nk naught. Okay, so far so good. We've got to this, basically equation, and now all we're going to do is we're going to sum over all the modes. So we're going to sum over k. And I've sort of left out polarization and a lot of fancy indices and stuff like this, but this is sort of basically what gets you here. what we can see is that if we take this h bar omega and put it inside this derivative, because omega and h bar, they aren't depending on the temperature, we ultimately get something that looks like this. So we have d h bar omega k in k naught over dt. And this is an energy. So this, what we'll call this the modal heat capacity. Because what we've done basically is say we're taking the temperature derivative of a energy, the energy associated with a particular phonon mode. And so this is the heat capacity, and it's evaluated at that local equilibrium temperature. So we have a heat capacity. If we kind of take everything here and combine this h bar omega with this ddt of n. And so now we have something that looks like this, where we have Vk squared heat capacity. And what we're going to do is just multiply the tau through. So we have a tau on this side and no longer a tau on this side. And this is all over here. And now we have gradient of temperature. And then this is all equal to, again, we've multiplied the tau over, and you'll see that this is basically equal to the heat flux on the previous slide. I'll go ahead and put that up just so it shows up if I can find the clicker. Here we go. So this part over here, this h bar omega v in k is equal to the heat flux. So we can go ahead and write down the heat flux. And this is a very fundamental definition for the heat flux. And then finally, you have this last little term over here, which is this nk naught. And what we have here is this is an even function of k. Omega is an even function of k. And v is an odd function of k. And so when we do a sum over all k, this term goes to 0. And so all of a sudden we have this thing here, and I dropped a negative sign, that looks very, very similar to Fourier's law. And in fact, what we can do under these assumptions is we can define this term here as the thermal conductivity. So we have K, the thermal conductivity is equal to Vk squared Ck tau. Great. So that is just an illustration of how you can go from the Boltzmann equation to the Fourier's law. And a lot of what happens in this nanoscale phonon transport theory is you postulate other different expressions for the intermediate distribution function, or the distribution function, and then you can arrive at various different transport laws that may be valid under certain conditions. So any questions at this stage? Because we're sort of through the math part. Hey, yeah.
After the result is correct, but on the left-hand side, you do local equilibrium approximation, replace nk with nk naught.
Yeah.
On the right-hand side, you said don't do that.
That's a really good question.
Justification on why you do it one side.
Yeah. I think that it's, obviously it's wrong from the standpoint of like we're making a huge approximation. I think that the idea here is that you're keeping this, let's see.
You can think of it as like a perturbative expansion in grad T.
We did the deviation from equilibrium. Grad T is already.
Yeah.
So then what's multiplied? So the thing on the right hand side is a deviation, and grad T is deviation. So then what's multiplying is the lowest order you take the equilibrium.
Yeah, I think grad T is, you're also kind of assuming grad T is small like that. And so you end up with both sides being first order. Yeah, excellent. Yeah. Any other questions about, yes? In this particular example, I just made it a constant. So it's the same for every mode, but people will often do this and say it's mode dependent. And then you can do all kinds of like first principles DFT simulations and figure out, well, what is the tau for the mode-wise tau and put it in. But just for the simplicity of this, I said, let's just have a single tau because it makes it easy to go through with the math. But that's a good question too, I think. Yeah. Yes.
Yeah, so maybe, so there's a lot of assumptions, approximations here. So how well does it work? Like if you put it in just experiment?
Yeah, that's a great question. What will happen is, you have two things. You have the basic form of Fourier's law, which is that the temperature gradient is proportional to the heat flux. That's one thing. The other thing is that the absolute magnitude of the thermal conductivity. There's a lot of systems where the form of Fourier's law holds. So you really do have a system where the heat flux is proportional to temperature gradient, but the thermal conductivity is modified. Like let's say you have a thin film. You're going to basically still have Fourier-like behavior, but you're going to have a lower thermal conductivity. But let's say you have a really complicated system with a lot of different nanostructures going on. You might actually have a situation where Fourier's law itself doesn't hold. And then you have to introduce, like, phenomenologically maybe, or through some derivation from the BTE, you might introduce like a second derivative of time in the heat equation, or temperature in the heat equation. And you might introduce like a second, the gradient of like the heat flux will come in. The Laplacian of the heat flux will come in a lot. This is like a very typical term that people will introduce, and you can get that out of the BTE under certain assumptions. So there's kind of
correcting the Q.
Yeah.
Plus the Laplacian. Exactly.
Yeah, and we'll get into that a little bit later too. But this is one of the things that you can do is you can show that under certain circumstances, the form is wrong. You actually need an additional term, a higher order derivative.
Is that like when you have large structures or you have small structures?
Small structures. This would be really small structures. And the idea would basically be if you have a really small structure, let's say this is TH, and then you have it on a substrate, the phonons are going to want to come in and sort of turn a corner to get out of the structure. And Fourier's law says that every phonon immediately out isotropically, basically. But in a very, very small nanostructure, that's not going to happen. They're going to go down and they're going to have trouble turning the corner because you don't really have a lot of scattering going on in the immediate vicinity of the structure. And this is where the Laplacian comes in. Is like it's basically acting like a viscosity in a Navier-Stokes equation.
But what's the length scale that compensates?
That's a good question. People will have some length scale out here because you need a length scale to make the dimensions work out. And this length scale, for silicon, it's like 150, 200 nanometers. And people will calculate, you can kind of think of this length scale as a weighted average of the phonon mean free path distribution in a bulk material. So it could be some sort of fancy weighted average that's on the order of the phonon mean free paths. Yeah. Great. Any more questions at this point? Because we'll sort of start getting into experiments and sort of novel theories of phonon transport. Yes.
I was also wondering, so this expression is very classical for the thermal conductivity.
Yeah.
So I imagine in small structures maybe, or low temperatures it breaks down.
Yeah, I think that is true. People kind of sweep this under the rug a lot. I think that a lot of times people are doing, the Debye temperature of silicon is like 600 Kelvin, and people are doing classical MD simulations at 300 Kelvin with empirical potentials. So a lot of times in the theory, I think it's like get an empirical potential and then just use the classical stuff.
Would be the form of N capture. It's sort of standard in what people would call quantum kinetic theory that it's this like the statistics enter into the collision interval and the equilibrium distribution. So that's sort of where it goes on.
Yeah.
But I'm also thinking like phonon quantization, low phonon.
Yeah. Yeah.
If you're talking about like a single quantum photon wave packet, then
like in small structures I can see.
Well, and one of the main things we're neglecting here is that these are all particles, they're not interfering. That is the big thing that's the first thing that comes in at really low temperatures is now you have some kind of like, let's say you have some sort of periodic structures and you're putting phonons through this. If you're at 300 Kelvin, you have some surface roughness here on the order of the phonon wavelength. So it's like nano surface roughness. You're totally incoherent. You just think about them all as particles. But now if you're at 5 Kelvin, the phonon wavelength is 10 times as long. And all of a sudden you can have interference between the phonons. And then you can have like band gaps open up in the dispersion and things like this. And so that's like the very first thing that kicks in when you ramp down the temperature is this idea of like coherent transport, and that's totally outside the BTE.
But that's pretty, I
yeah.
imagine that you can just say you're going to count by modifying omega of K. The dispersion.
Oh yeah, you can do that. A lot of times when people will do coherent transport, they'll literally, at a certain point, you're just dealing with acoustic waves that happen to also carry heat. And so you're doing it in COMSOL. Like they'll be in 4 Kelvin doing this all in COMSOL, and they'll say, okay, this is the modified dispersion, and this is the thermal conductivity we predict from that dispersion, and this is what we observe in the experiment as a function of temperature, and oh, look, it matches up, kind of thing. So it almost becomes easier when you have coherences because you're so low temperature, you're just doing acoustics at that point, but with thermal phonons. Yeah. Great. So now we'll get into some of the experiments. Let's see, we've done this. The last little remark here is that, so this whole framework where you're writing down the thermal conductivity as a sum over microscopic properties, this works extremely well in bulk systems. So if you have a system that is much larger than the mean free path of the phonons on a time scale that's much longer than the lifetimes, you can do DFT, you can put it all in the equation, and you can get something out that looks very, very similar to the experimental measurements. So this was all starting in mid-2000s, around 2004, 2005, when the computation power came online, and people were able to basically predict the thermal conductivities of silicon and germanium and increasingly a much larger variety of materials in bulk extremely accurately through just DFT calculations, and then putting them all into this thermal conductivity. You can sort of do a whole PhD on this where you take 50,000 different candidate thermoelectric materials and you say, what are all the different thermal conductivities of these possible thermoelectric materials? And then which ones look like they might have the most advantageous thermoelectric properties? And then let's try fabricating 10 of them. That's sort of a very, very good framework for this. But the problem is that once you have length scales on the order of the phonon mean free paths, time scales on the order of the phonon lifetimes, this framework no longer works so well. You have to either modify the thermal conductivity, or you have to basically start using a totally different transport equation. So now we'll get into the nanoscale phonon transport. And I'll do a first example. This is second sound. And second sound is basically, you can think of it as like in first sound, the density is oscillating of the atoms, and that's sound propagating in a material. In second sound, what we have is the temperature is oscillating. And so this is a really interesting phenomenon because if the temperature is oscillating, the temperature is behaving as a wave. And if the temperature is behaving as a wave, you can carry heat away from a hot spot in a sort of pulse rather than waiting for it to diffuse out from a hot spot. So this is a sort of thing that has become very exciting in the last 5 or 10 years. It starts out with, you have some very arbitrary initial distribution function here. And this is like, you just excited your sample with a laser, and it's like 100 femtoseconds later, and you have no idea what's going on. The electrons and the phonons are still, you're still passing electrons or energy into the phonons from the electrons, and you have a really, really crazy distribution function. And then you assume that on some fast time scale, and fast can mean a lot of different things here, you have an intermediate distribution function to which you relax, which is not the Bose-Einstein distribution. Here you can see we have a little drift term in this intermediate distribution function. And this is sort of one of the core approaches to nanoscale phonon transport, is you assume you kind of have 2 timescales. One, a fast timescale to relax you to some intermediate distribution function, and then a slow timescale over which that intermediate distribution function relaxes to equilibrium, to Bose-Einstein. At that point, you're sort of back to...
Physically, what is there some argument for like, what scattering process one of these things corresponds?
Yes. Yeah, this is in the sort of classical second sound. What you're saying basically is that you have a lot of normal scattering. So this is where the crystal momentum is totally conserved. You're not adding in reciprocal wave vectors or anything like that, reciprocal lattice vectors. You have a lot of this normal momentum conserving scattering that gets you here. You can see that basically this is an additional momentum term, this drift term. And it's something that can't be relaxed by normal scattering, because if you're just scattering normally, your crystal momentum is still conserved and your phonon distribution is drifting along a certain direction. So the basic assumption here, and I think y'all might have talked about this a couple days ago, is you have a lot of momentum conserving scattering events. And it's very analogous to electrons that are happening that get you to this, but you don't have a lot of resistive ones. And so you get to this drifting distribution where the whole distribution is drifting over, and then the resistive scattering starts to kick in on a longer time scale. And this is some, oh yeah, go ahead. Yeah.
So I was just wondering,
Yeah.
you have the intermediate one even with club, or?
The idea would be like you could write down like a tau n and a tau r, and you would say that tau r is much greater than tau n. Like you would say something like.
So if that's the case,
Yeah.
you will get the intermediate one first.
Exactly, yeah. So you'd say something like this. And then when you have this, it takes a long time to have resistive scattering. It takes less time to have normal scattering. And so you get this intermediate distribution function where the normal scattering has relaxed you to sort of a well-behaved function that you can do math with. That's sort of just all the phonons drifting in a certain direction with the crystal momentum they had to start. And it takes longer to have the resistive scattering kick in and bring you to equilibrium. And I think this is really, really similar to what you write down with electron hydrodynamics. And that's probably what it's inspired it, basically. And so in this particular case, there's other ways that you can get to second sound, and I won't go into all of that, but this is the classical way that you get to second sound as you assume this. Yes?
In terms of actual seconds, picoseconds, femtoseconds, do you have a typical, what is fast, what is slow?
Yeah. Let's say that the electrons and the phonons are passing energy between them, and like, because let's say you start with a laser pulse and it's like a 10 femtosecond or 50 femtosecond laser pulse, and that excites the sample and that excites the electrons. And then the electrons are scattering with each other over the first few tens of femtoseconds. And then over around like the first picosecond, they're scattering with the phonons and sort of equilibrating with the phonons. Maybe a few picoseconds, it depends on the material. And then I'm sort of making this up a little bit, but it would sort of be reasonable to see here that you would have tens of picoseconds or a few picoseconds to get to this drifting distribution. And then in the experiments, and I'll show these experiments on the next slide, this kind of slow time scale with the damping is, a few nanoseconds to tens of nanoseconds. But you do have to kind of tune a temperature window to get that nice kind of cascading of timescales. Yes. It's kind of just like a arbitrary velocity. It kind of represents the imagine of a bunch of, you have a net crystal momentum going in a certain direction. That's kind of what it's representing. In my understanding is like there's a net crystal momentum traveling in a certain direction that can't be canceled out by resistive scattering events. And so the whole distribution is basically moving over.
You can think of it as sort of like a fluid velocity. Like that intermediate distribution is describing a fluid where the momentum is conserved in all of the phonon collision.
Will that be a medium dependent, or would that be some, like just intrinsic to system? I mean, how to get it?
Yeah.
I just want to have a substitution.
Oh yeah, I don't really know like values for this. Someone might be able to help me out here for electrons. I think that, let me see what's a good way to describe it.
The values for what?
Oh, like what would be like a system? Does U change with the system, or I think it's.
I mean, I would say it's it depends on the strength of the temperature gradient. Right?
Yeah.
So this U, this U would be proportional roughly to the thermal conductivity times.
Intrinsic factor.
Yes.
Yeah. Like if you hit the system really hard, I think, then you get a really large U. Exactly. Yeah. I would sort of think of it as like the net crystal momentum of the whole phonon distribution in the material. So it's like a net, how much is the distribution got a non-zero total crystal momentum in its non-equilibrium state. And if you hit the system really hard, you have a really high initial non-equilibrium crystal momentum. And if you don't excite it as much, it's a less of a crystal momentum. But it's not something that you would calculate from like oh, we're using silicon, so we have this value. It would, I think, be something like what is just in terms of like, you could sort of think about it as the second moment. If you excite something, you're going to give it a deviational energy. This would be like the deviational crystal momentum that you gave it when you excited it. And the cool thing here is that if you take this distribution function, you just put it back into the Boltzmann equation, you get this modified, oh shoot, I forgot to change the slide. This should be a second derivative of temperature with time. So you get this, basically you get a wave equation for temperature. And this wave equation is saying that now, and it's damped because you still have a dt, but this should be a dt squared dt. And this is a damped wave equation for temperature. So this means that part of your thermal energy is actually propagating as a wave, and it's propagating with a particular wave velocity that's distinct from the acoustic velocity, so you can actually measure this in an experiment. And this is different than the heat equation, and people got excited about this because they thought, oh, well, this is going to allow us to move heat around in the same way that we would move a lot of other things that travel as waves much more easily than something where we're waiting on a diffusion process, which we can't really control. So this is why people are excited about second sound. Yes.
To get the damped equation, do you use the Umklapp scattering still, or?
Oh, great question. This would basically be assuming that the Umklapp scattering is negligible on the time scale of the damped wave equation. But I think that what you're saying is that this dt, I think this does kind of come in. I'd have to think through. I think that is basically representing the graph. So it kicks in scale. If that's completely not damped, I think in the limit where you set tau r to like infinity, then you get dt goes to 0. Yes. Yeah.
Oh, okay.
Yeah, like I think if you took like a limit where we're just going to say this is just going to infinity, then I think you end up with a pure wave equation, which is, I think that's right. Yes. Oh yeah, do you have a question? Yeah. Oh, that's time. Yeah, I messed up this equation. This should be a second derivative. So it should be a second derivative, and this should be time. And that is basically giving you can use that as like the characteristic time scale associated with the. Yeah. Great. Oh yeah.
You get it from this. This is the analog of sort of the Euler kind of equations. You don't have a viscosity.
Right. And we'll get to a viscosity equation later. Like this is kind of like, we talked a bit about this term earlier. This is like the other, if you just sort of look at what terms could I add in, this is the other term. And this has the tau SS. So this is the second sound. So this is the kind of analog in like you were talking about for Euler. And we'll talk about viscosity in a bit too with some experiments.
But is tau SS related to tau N, or probably not, right? So what goes into special for tau SS?
It's a good question. I think that tau SS, another way you can derive this that I'm thinking of, and this is called like driftless second sound, is you can assume that all of the phonon processes sort of have a characteristic relaxation timescale that's all pretty similar, and that ends up being tau SS. I think that depending on how you derive it, you can get like tau SS is different combinations of tau R and tau N, but I might be.
I think it will be dominated by tau R. I think a nice way to think of that equation is you just divide it all out by tau S.
Yeah.
And then the coefficients of the second derivative and the gradient are basically thermodynamic functions. And then the dissipation comes from the 1 over tau SS.
Yeah.
Term.
Yeah. Yes.
I understand this is kind of you're using the laser exciting the electrons to a higher energy state and trying to kind of dissipate the energy.
Yeah.
And because the phonons have some kind of bottleneck or something, this essentially takes longer time, and then somehow this initial equilibrium is your fast time scale, and then the slow relaxation of energy through the phonons is the slow time scale, or is it is it actually already energies that are all in the phonons, and your phonons going back to equilibrium is a slow time scale? Like which one of the two is
Good question. It's the second thing you said. We're no electrons at this point. It's just sort of the example I was giving is, let's say you use an optical laser to excite the electrons, then they pass energy to the phonons, and that's going to be a really weird distribution function. You don't really know what that's going to look like. And then let's say now the phonons and the electrons are totally in equilibrium, but we still have a weird phonon distribution function, and we're relaxing back to phonon equilibrium. Yeah, and so both the fast and the slow timescale are phonon timescales, but just different types of scattering. Yeah. Yes.
Are we assuming that we're only occupying a small part of the Brillouin zone in terms of the phonon occupation?
Oh, good question. I think what usually gets assumed in these derivations is you assume that you're reasonably close to equilibrium. If that's kind of what you're meaning. I think like
no, what I'm asking is
yeah.
like this k dot u is not invariant if I add a reciprocal lattice vector.
Oh yeah. You're assuming, I guess, that the phonons have pretty, like the phonon scattering is mostly normal, and so if it's mostly normal, that means that you do have pretty small k vectors, so you're pretty low in the Brillouin zone. That's totally correct, and that's part of the reason why people generally do this at low temperature, because I think that does eliminate a lot of this high k phonons that are producing the reciprocal lattice vectors that are causing the umlaut scattering. So I think that that's totally right, and that we'll see is people started at first they thought this is like 10 Kelvin thing because of that reason that you mentioned is that it's something where we pretty much have to go to low temperatures to see this, because otherwise we are going to have, but that's a really good question. Otherwise we are going to have phonons with very large wave vectors that are going to do resistive scattering. Did you have a question? Okay. Great. So going into some experiments, people originally thought this was, like we were just talking about, something that happens at really low temperatures. It was observed in the 70s, and people eventually kind of wrote it off because they said, well, we can't see this above 10 Kelvin. And so it's maybe technologically not all that interesting. Then in around 2015, people did a bunch of calculations on graphene and graphite, realized that you can get this kind of imbalance between normal and resistive scattering in graphene and graphite. And as a result of this, they were able to observe this kind of oscillation in graphite at 100 Kelvin. And now they've pushed that up to 200 Kelvin by making it even more pure, because the more pure the material is, the less sort of resistive scattering you have from impurities. This is kind of the time scale we were talking about. As you can see, these oscillations are damping out on like the single-digit nanosecond time scale in graphite. So we have a very damped wave oscillation that's being seen here. And then even more recently, people are talking, well, maybe there's different second sound. This would be called, previously we were talking about the drifting distribution. Now people are talking about driftless second sound, where you don't have to have this particular distribution. We don't necessarily have to have a particular kind of phonon scattering. And so you can see this in materials even where you do have a significant amount of resistive scattering. Yes?
Is oscillating as the case?
Yes. We can talk a little bit real quick just about, because we'll get into the experiments more, but the idea is you cross two laser pulses on the sample. So you have laser pulse 1, laser pulse 2, you cross them on the sample. What that gets you, because the laser pulses interfere, is a sinusoidal heating profile. So you have a heating profile. Let's see, we can probably move this up a little bit. You have a heating profile that looks kind of like this at time 0, where this is T hot and this is T cold. This is created with the interference of two laser beams. And now you're going to have the evolution of this back to equilibrium. And of course, equilibrium looks like this. In a normal Fourier, where this is just T0. And in a sort of normal Fourier problem, you would just have the peaks would get smaller and the values would get higher until you got to this. And in second sound, what you see is that these actually switch. So at some intermediate time scale, you have this. In this particular experiment, where the hot and the cold regions of the sample have actually changed places. And that's what's going on in this experiment. Yes. This is position. So let's say this is temperature and this is X. And then this is, let's say this solid curve is T0, and then this is T equals T1. So some later time. This is kind of what you would see in the experiment is, in this particular experiment, you have a sinusoidal oscillation, and then you have the reversal of the hot and the cold areas as the temperature propagates as a wave rather than diffusing. Diffusion, you would just see that this would gradually relax to 0, and in second sound, they actually switch places. Yes?
This process within the laser spot, right? Within the interference.
Oh yeah, this is all within an interference spot. So the sample would look like this. You just have some piece of graphite, and you have a laser beam coming in here, and you have another laser beam coming in here. And then you have some spot, and then you have interference fringes. So the distance between these two fringes, a lot of times, is on the order of the phonon mean free path. And so that's like, maybe people are shooting for 300 nanometer interference fringes or 500 or micron interference fringes, and then over a millimeter or half micron spot size.
Is that T1 is like some related to with the tau R or tau? Oh, I mean, how that
This would be a time scale. I mean, I guess this was just sort of drawing an example of like, ultimately you're going to have a decay back to equilibrium with this tau SS, like Andy was talking about. So, you know.
second wave is appearing.
Oh, where the second wave appears. This has to do with basically the velocity of the wave. So second sound is going to propagate at some characteristic velocity. And this velocity is a kind of interesting weighted average of the acoustic velocities. So like there'll be a velocity of second sound, and it's equal to, let's say, some function of VL and VT across all the different polarizations, stuff like this. And this is kind of how they detected, is in this paper they said, well, we looked and this isn't the acoustic velocity. The acoustic velocity is faster. And the acoustic velocity is what like a ballistic phonon would travel at. And so this second sound velocity is kind of a weird weighted average of the actual acoustic velocities. Part of the way they find it in experiments is that changed velocity. You can see that here too. This is the experiment from the 70s. These are the longitudinal and the transverse pulses arriving with just ballistic phonons traveling with longitudinal and transverse velocities. And then here's the second sound pulse arriving, and this is arriving sometime later. And the second sound velocity, because the second sound velocity is a little bit slower than the ballistic velocities. So that's part of how they detect it. Yes. Great question. The probe is actually in the exact same spot as the pump. And what you're doing is you're diffracting from this sinusoidal profile. You can imagine if you have a sinusoidal grating that you've put on the sample, you can diffract from that. And then a little piece of your probe light is going to diffract and go onto a detector. And so if the sinusoidal grating's there, you see it. And if it's not, you don't. And that's kind of what they see here in this signal is at this point, the grating is gone. And so you have no signal because there's no diffraction. But you look at the same spot on the sample. Yeah. Yeah, cool. Yeah, we can always go back to that some. So now we're going to talk about confinement. This is sort of the opposite, not the opposite, but the sort of sibling of what we were talking about with second sound is now we're talking about this Laplacian term. And the idea here is, well, what if you have a system with dimensions that are smaller than the phonon mean free path? And to give you an idea of what kind of size this is, these are calculations for silicon that were done about 10, 15 years ago. The plot is bulk silicon. What is the mean free path distribution of the phonons that contribute to thermal conductivity? So they looked at basically which phonons contribute the most to thermal conductivity, and what are the mean free paths? What's the average distance that these phonons at a bulk silicon crystal? And you can see it starts around 10 nanometers and it goes up to 10 microns. So this is one thing that makes phonons really hard, is the mean free path distribution of phonons is extremely broad relative to electrons. Electrons, you generally have a pretty narrow mean free path distribution. Phonons, it can be 3 orders of magnitude in a lot of materials. So you can already, according to this calculation, have a 5 micron piece of silicon, and you will no longer see the bulk thermal conductivity even at room temperature. And that's a huge dimension relative to the size of a transistor. That's 1,000 times bigger than a transistor. Where you're going to start to see size effects, confinement effects on thermal transport. And this is a big motivation for why people are looking at this now, is Moore's law and semiconductors, is that you can see here, this is kind of a plot of various metrics of semiconductor industry since the 70s and up to the present day. And they're still packing on more transistors per chip here, but they're no longer increasing the clock speed. The clock speed is sort of maxed out. And the reason that the clock speed has maxed out is that you can't evacuate the heat fast enough to run it at a higher frequency because your computer will catch on fire. And so this is a big motivation for this research, along with a lot of other things like energy efficiency, energy harvesting, stuff like that. And this stuff becomes very relevant on the length scales of a transistor. So we'll sort of take the first example here of this confinement, and this is a thin film. So sort of the simplest geometry we can imagine. And we're doing this all in steady state. We're holding the top of the film at a temperature T2. We're holding the bottom of the film T1. And we're asking what's happening across the film. And the thermal conductivity is going to change once you make the thin film pretty small. And naively, what we could do is we could take this expression for the thermal conductivity that we derived, and we could say if the mean free path is, we're just going to take the bulk mean free path distribution. So we know from the previous slide we have this thing, we can solve for it. We're going to take the bulk mean free path distribution. We're going to say all the phonons with a mean free path less than the film thickness are unaffected. They're just going to do whatever they were doing. All the phonons with a mean free path greater than the film thickness, so bulk mean free path greater than the film thickness, they're going to truncate. They're going to scatter on the film boundaries. This is sort of the most naive way you can do this, and it works shockingly well for a thin film. Yeah.
What is the lambda k? Is that still an arbitrary function?
Oh yeah, I'm just calling that the mean free path of mode k. So it's like a statistical quantity of mode k, and if it has the reason I put a bar over it was just that this is like a modified mean free path depending on whether the bulk mean free path is larger or smaller than the film thickness. Yeah, so like the simplest thing you could do is just say, I have this distribution. Let's say that my film is 100 nanometers thick. I'm just going to separate the phonons into 2 categories. One, which is going to scatter on the film if it's greater than 100 nanometers. It's going to scatter at the edge of the film. And then the other one, which is going to scatter internally if it's less than 100 nanometers. And that's, of course, going to reduce the thermal conductivity if you make the mean free paths smaller. So all we're doing is just making the mean free path smaller in this equation, keeping everything else the same, and it works pretty well. You can get a lot more sophisticated than that. You can also do computational simulations. You can do molecular dynamics simulations. You can solve for temperature profiles. The problem is that and these temperature profiles are pretty accurate in terms of what's observed in experiment. We can see if like this experiment that are pretty similar to what these temperature profiles predict, where you kind of have like a bulb-like shape. And this is what we were talking about up here, is the temperature is not, the heat is not spreading out isotropically when you heat a hot spot on the surface. It's actually sort of scattering insufficiently, and it's spreading out in kind of a bulb-like shape. And so you can do these sophisticated computational simulations, but if you're doing more than a few million atoms, it starts to become, I don't know exactly where the cutoff is, but it starts to become very difficult above a few tens of nanometers to solve even with really advanced computers. And then you can get even more complicated. Like what if your system, yeah.
Oh, so that's an MD.
Yeah.
That's not, like if you solve the Boltzmann equation with some non-trivial collision integral, is that sort of I would think that's maybe computationally simpler than MD, but still would capture that.
I think you can kind of get that in a Boltzmann equation if you make the right approach assumptions. this is basically the geometry we're looking at here is you have T cold on the bottom. And then you have a particular heater, which is shown in the image that's at T hot. And then it's like, what is the temperature profile underneath the heater? And this second row here, this is the solution to Fourier's law. And that is, you can see it just fundamentally doesn't capture it, even if I make up any thermal conductivity I want to in the world. And then this one is the MD solution. And I think this is where we get into, well, if we add this Laplacian term, all of a sudden it starts to look a lot more like the MD. And that's coming out of the Boltzmann equation. So it is a big game of how can we do a mesoscale simulation that actually matches the experiment, matches reality reasonably well without having to do 50-hour-long simulations. Yes?
Does this have anything to do with the thickness of this 9.8 nanometers? Like, what if it was infinitely deep? Like, presumably you still have this bulb profile.
Yes, you would. You would still have the bulb profile. The reason this is 9.8 nanometers thick is so that the molecular dynamics simulation could be performed. But if you did it with an infinitely thick substrate, you would still see a bulb profile. And so I was kind of conflating two things because this is like, this first example on the top here is a film. It's just T hot and T cold, and that you're just going to have, it's like one-dimensional. But here it's two-dimensional because we have a heater of some finite size. And then no matter how thick you make the film, if the heater's really small, you're still going to see a bulb. Yeah. Any more questions about this one? But really good question. And so then it's like, well, what if you have a really crazy geometry? So this is this example, and we won't go too much into the exact details of this, but what's going on here is you have crystalline silicon, and you've punched holes in it at some regular spacing. So you have a lattice, and then there's pieces of the lattice that are missing, spheres of the lattice that are missing, and this is what's called a metalattice. And now all of a sudden you have multiple different potential dimensions you could use in your Boltzmann transport equation. You have the size of the pores, you have the distance between the pores, you have the next size of the smallest distance between the pores, you have whether the pores are staggered or they're aligned or things like this. So all of a sudden you can't just do some simple truncation of your mean free path distribution. You have to do something more sophisticated. And the original idea behind this, just to connect to something earlier, is people thought that this would be a great way to see coherent phonon transport because you can put up a regular array of pores and then cause the phonons to interfere with each other. But at room temperature, it's really hard to do this because it's really hard to fabricate this with a surface roughness of less than a nanometer, which is really what you need to see coherent effects at room temperature. But it works really well if you're looking at just basic sort of incoherent phonon transport with the Boltzmann equation, what happens in this sort of test bed geometry. And this was also a candidate thermoelectric material, with the idea that if you have a really low thermal conductivity and you leave the electrical conductivity somewhat intact, you could maybe work with silicon rather than some really exotic material to make a thermoelectric. So this is a lot of times what this will be called as phonon hydrodynamics in the literature. The reason behind that is because you have a viscous term, you can get things that look like the Navier-Stokes equation. It's kind of the same game that you're playing before where you suppose an intermediate distribution function, you rapidly relax to something that has some thermodynamical motivations, and then you can plug that into the Boltzmann equation and you get out modified transport equations. And these modified transport equations produce temperature profiles and heat fluxes that look a lot like what we see in experiment. The idea here is that if you have a really large bulk system, this equation will still give you a flat sort of heat flux profile that looks very similar to what Fourier would predict. And as you increasingly confine the heat flux between two pillars or between two, sort of pores in the system, so you have a small channel, you start to get a Poiseuille-like profile. And this is a really specific shape that shows up in hydrodynamics. It's a parabolic heat flux profile. And you can go all the way down and get things that start to look a lot more like hydrodynamics. You can actually see this in comparing to molecular dynamics simulation. So this is some recent work is you have diffusion, you have a ballistic prediction, and the ballistic prediction, what we're looking at here is the heat flux magnitude. So brighter colors mean you have more heat passing through that area. Darker colors mean you have less heat passing through that area. With a ballistic kind of approach, you have shadowing between the pores. So maybe you see this effect where basically if the heat is going from the top to the bottom, you'll have sort of a shadow by every pore. You don't really see this as much in the molecular dynamics, and you don't see it as much in the hydrodynamics. All of the models are pretty good at predicting the bulk conductivity. So it can be very difficult, or it can be pretty difficult to differentiate between models like this just using a global metric like the thermal conductivity, because everybody predicts that the thermal conductivity goes down at the nanoscale. So how do you differentiate between different models? You need access to some of these microscopic variables. And that's where a lot of these experimental techniques come in. So kind of any questions on all this? Because I'm sort of going a little bit quick just so we get through for coffee.
Can you
yeah.
go back just a couple slides?
Yeah.
Yeah, that.
Yeah.
Yeah. So we have Q equals to something. That's with Q. Are you solving this equation for Q?
Yes. Or for temp. Yeah, exactly. This is nice because, well, of course, this first two terms are just Fourier's law, and this is the additional term. This is steady state. So we could have a dq dt in this equation if we were in non-steady state. But the nice thing about this equation is you can do it in COMSOL. You can do it in finite element modeling, and that's really attractive to engineers, designers, things like that, is you can solve these kinds of things in minutes on a laptop or on a reasonable desktop as opposed to doing MD. Yes.
But you just mean from this, you would get time derivative of temperature equals to, rather than just Laplacian of temperature, you'd get the fourth derivative of temperature?
I think you would get a term that basically, you would get something like this in this equation if you had it as non-steady state. And this is dq dt, but if you turn this into a heat equation, this would give you the second derivative of temperature. So this would give you the second sound. Because this is sort of like, before I was working with we had the heat equation, and now this is a equation. It's kind of like a momentum balance equation, like Navier-Stokes. And so this would give you the wave-like oscillations if you had that in there. But in steady state, it just goes away.
If you added that.
Yeah, if you add that term, that'll give you like a damped wave-like. Once you go and combine it with conservation of energy and turn it into a heat equation analog.
But I meant also, like, if you just take continuity equation for energy, then you get time derivative of the energy equal plus divergence. Normally that gives you just Laplacian of t.
Yes,
time of t gives you equals to Laplacian of t, but now there's like
Yeah, but this is the Navier-Stokes equation. So you have dq dt. So you have your continuity equation.
Yeah.
if you add that.
Yeah. So this is the steady state.
This is just steady state of like, well, if we just hold the temperature at either side of the system, hot and cold, what happens? And what steady state do we get to? And that's this equation. I just left out this term, which would give you the.
Yeah, like again, I would say you divide by a time scale and kappa. It's like the grad T term is like gradient of pressure. The L squared, that's viscosity, and then the Q over tau is like friction.
So Q is like independent dynamical. Roughly speaking. Okay.
Right. That's it. There's two equations now.
Yeah. So that's and then energy conservation is always the same for all this. It's always that that you have that you add into these to get to the heat equation. So we have this. So this is one way you can look at this is we use these extreme ultraviolet sources that Margaret was talking about. And this is basically the experimental version of the MD simulations we were talking about. But this came first, and then it's like, well, how do we explain the crazy results we see here? And the idea is you have a silicon substrate, pattern nickel nanowires on the silicon substrate in a one-dimensional grid. These nanowires have some pitch and some line width that's small compared to the phonon mean free paths. You heat the nanowires, but not the substrate using an infrared pump laser. So you're not really depositing much energy in the silicon, but you're depositing a lot of energy in the nickels. Then you come in with an extreme ultraviolet probe. And why is it important that it's extreme ultraviolet? It's important because you have a really short wavelength, so you can diffract from structures that are below the visible diffraction limit. It's also important because the extreme ultraviolet can be tuned away from these core electron resonances. You're really pretty much sensitive to the density, the core electron density of the material. And this is really nice because you're basically only measuring how is the density changing and what is the height difference between the nickel and the substrate? How is that evolving with time, rather than like, what are all my valence electrons doing at 5 picoseconds after the excitation? So you're very sensitive to the phonons. You come in with the CUV and you can measure a dynamic diffraction pattern because the EUV is a very short pulse. And so if the EUV is a very short pulse, you're sort of coming in measuring a dynamic diffraction pattern at various delay times after the excitation. And you get these basically delays as a function, you get these delay curves as a function of diffraction efficiencies as a function of delay time. And this is really interesting result from about 10 years ago. And the result is that if we have two sets of nickel lines, they have the same line width. So we have a 20 nanometer line width in both cases. This is like e-beam lithography, sort of approaching transistor scales. If we have one here on the top or let's say here on the bottom, let's start here, with a 400 nanometer pitch. So these lines are pretty far apart. They cool pretty slowly. You can see that, after 100 picoseconds, they're still pretty hot. If you have the same lines, but now you put them closer together, so you have an 80 nanometer pitch instead of a 400 nanometer pitch, you can see at 100 or 1,000 picoseconds. So sorry, 1,000 picoseconds, they're cool. The diffraction efficiency has gone back to what it was before the excitation. This is really counterintuitive because you're putting the same amount of energy into each nickel structure. The pump is not changing. And the pump is just coming down and putting a certain amount of energy per unit volume into every nickel structure. But the nickel structures that are closer together are cooling faster than the nickel structures that are further apart. You would never see this with classical Fourier's law, And so this is sort of an interesting result, and this motivated a lot of the molecular dynamics work and a lot of the subsequent mesoscale hydrodynamics work of how do we explain this kind of effect. And sort of part of the answer is, well, if you have phonons from adjacent structures that can see each other, that can scatter with each other, you can scatter preferentially into the cross-plane direction. And that can cause you to evacuate your heat more quickly than if you have more isolated structures where you can't have phonon scattering with hot phonons emitted from adjacent structures. So that's a really interesting experimental result. One of the things that got me really excited about looking at nanoscale phonon transport in grad school. So that's pretty much all we've got for today. I know we're pretty much running out of time. The phonons, just a summary, phonons appear in all different contexts. Like a 4 Kelvin phonon in a quantum experiment is very different than a 300 Kelvin phonon in a thermal transport experiment. You have to use all different kinds of frameworks to represent them. Very hard to study phonons because you don't have the same ability to manipulate them as electrons. So we're behind in terms of understanding the theory of nanoscale phonon transport. And it's really important for a whole bunch of different technologies like semiconductors, quantum materials, all kinds of things like that. So yeah, I'm happy to, thanks so much for coming. It was really fun to give a talk to y'all, and I'm happy to talk about anything after or take questions now, whatever you want to do.
Okay, we had some questions during the talk. Are there any more questions?
Yeah.
Always happen at the photon time scales, or are there cases where it's like more like slow creep of defects?
What do you mean by slow creep of defects? Okay. I'm trying to, so you'll have a lattice expansion parameter, like a thermal expansion coefficient is usually what we're working with. Of if you change the temperature by this much, how much does the lattice constant change? That's kind of what we think about. Of course, you can have all kinds of strain effects and things like that, depending on the fabrication that we have to worry about. You, of course, also have lattice expansion due to acoustic waves. So like if you have a longitudinal acoustic wave, that is going to change the lattice. you might be able to see it here a little bit is there are oscillations in here that you can do sort of Fourier transforms, get oscillations out of this data, and that's an acoustic wave propagating across the surface. That's another way the lattice can expand without really changing the temperature. So there's stuff like that. I'm sure there's also lots of really exotic stuff, but the main things we think about in these experiments are the phonon thermal expansion due to the actual temperature change, and then the surface acoustic waves that are propagating. And the surface acoustic waves in this particular geometry, they have a wavelength equal to the spacing of the structures. It's sort of like a resonant mode that you get. Yeah, question. Oh, yeah.
How far? So for example, those weird dissipation, slow dissipation when it is far apart, is that something to do with what is like the matrix material versus the nanowire material, or is there any more understanding of it?
I think that people haven't tried this on a lot of sort of like more exotic materials. Silicon is seen silicon, like sapphire, things like this. It's really hard to see this with a visible laser, which makes these experiments kind of difficult because we're looking at pretty short timescales. And if you're working with a visible laser, you see a lot of electronic effects at these timescales that can make it pretty hard to actually study what the phonons are doing. But the theoretical understanding is definitely advanced. And at least as far as I know, there's a lot of companies that are trying to look at this now, basically. Like there are companies saying like, well, we can model a single nanostructure in isolation with the Boltzmann equation, things like this. We have trouble now when we have a lot of nanostructures close to each other. How do we model this? So this is like a really relevant problem in industry right now too. Because it's a lot easier to treat like an isolated sphere in a medium than to deal with like periodic kind of excitations. Yeah.
So as you state, you're increasing the nanostructure distances, is heat is dissipating faster, or it is cooling down faster.
Yeah.
Does it have anything that you are increasing the area per unit length?
Good question. Yeah, we've tried sort of both ways. In this case, we're injecting a constant amount of energy per nanostructure, but the energy per unit substrate is definitely increasing in this closely packed case. And we still see it cool down faster. We've also tried a situation where we fix P or we fix the duty cycle. So we fix the ratio of nanostructure to substrate, and then we decrease both the line width and the period of the nanostructures in ratio. And in that case, you also see an increased transport efficiency when you make them together. But that's a really good question. It's sort of been tried both ways. One way is constant amount of energy injection per unit substrate. Another way is like constant amount of energy injection per unit nanostructure, and we see it in both cases. Yeah.
How do you achieve the delay time? So like, how do you change the arrival time of your UV laser?
Great question. In this case, what you do, EUV, in a vacuum chamber, so you change the arrival time of the pump. So the infrared pump is coming from the same laser that creates the EUV, and you make the pump get there earlier. And then it's like the optical delay line, like you have a retroreflector meter on a stage and you pull it back and forth. It's from the same laser, yeah. Yeah, that's really crucial to getting it timed up well. And so the high harmonic generation that Margaret was talking about yesterday, we take 90% of the laser and use it for the high harmonic generation, and we take 10% of the laser and use it for the pump, because you don't need all that much energy to make a nanostructure hot. And so we split it with the beam splitter. Yeah.
Okay, maybe so on the speed of second sound, like I guess in these materials, how do you compare to just like the the velocities of the S&P or LNT?
Yeah.
You want to call them, like just the elastic waves.
Yeah, it's slower, but I think it does vary by material. But
is it like so much slower that you could kind of ignore the usual elastic waves, or is it possible that there's kind of interaction between?
Yeah, there is like sort of correct for like and stuff like that I haven't into too much, but I think it's like, let's say like on the order of a factor of 2 slower. We can kind of look at these plots and like it's in the factor of 2 kind of range of This is longitudinal pulse arriving. This is transverse pulse arriving. This is second sound arriving. So it's like around a factor of 2. But it, it varies, and it's kind of like a weighted average. There's like a square root of 3 in there somewhere for 3 dimensions.
I guess I'm asking in part just for, like, I think for this experiment, I think that interpretation seems reasonable.
Yeah.
For the experiments where the way I would think of it, you're like, essentially, you prepare a perturbation, at a fixed Q, and then you ask how it relaxes.
Yeah.
There, I guess the conditions, like this is why in physics we don't teach elastic solids anymore, because the PDEs are too annoying. And like you would have boundary conditions that mix all of these different modes in complicated ways. I'm wondering kind of if that physics could pollute some of these experiments.
I'm not aware of anyone really considering that okay, there is a paper I'm aware. I can send you a paper, but I think people have looked at this way back in the 60s. And I think nowadays it's like, well, in the experiment, at least, like we saw this oscillation, and we checked that it wasn't the acoustics, and we're good. And I think that is, and we did a bunch of other simulations to show that like our second sound simulations look like our experiment. But I think that's a really valid question of there are these elastic effects of coupling that people have sort of forgotten. Like not to think. Yeah, question?
Structure that you have, right? So in this case, aren't you also just measuring some kind of average, or is sensitive to the actual structure of the system on the last example?
Oh, last example, yeah. Oops, the slide's gone. It's the EUV wavelength is comparable to the structure, but it's generally still a little bit shorter than the structure. So you can still diffract from the structures. Yeah, exactly. So like we'll see, it really enhances the signal a lot to be able to diffract rather than just do a transient reflectivity measurement. And so let's say like a typical thing is maybe we have a 200 nanometer pitch or 150 nanometer pitch of the structures, 100 nanometer line width or 50 nanometer line width, and our EUV wavelength is like in the 20s. So it's 25 to 30 nanometers EUV. And so that you still get to diffract, but that is like a question of if you want to look at a 10 nanometer structure, you need to do a different high harmonic generation process to get even shorter wavelengths. Yeah. Yeah.
If there are no more questions, let's thank Brett.